So after all those preliminaries, it's finally time to describe the RSA Cryptosystem. So this is named after Rivas, Shamir, and Alderman, who were all at MIT in the 70s and came up with this idea. So it's public key cryptography, so there's going to be some public information and some private information. And so, the basic idea with public key cryptography is there's some public information that lets Alice encrypt a message to Bob, but Bob is the only person who has the private information that allows him to decrypt the message. So the setting here is you have two big primes. So number theoretically, it all works if P and Q are small too, but in practice, we need to make P and Q big, and the reason is that N is going to be public information, but P and Q are going to be private information. So we need P and Q to both be at least 1,000 bits long for it to be infeasible to just factor N to get P and Q. Okay, so there's some more public information. So N is public, and also this little thing E, and E is the exponent. That's what E stands for, and E can be any number relatively prime to phi of n. By the way, that phi of n is also private. So it's thought that there is, phi of n is equal to p minus 1 times q minus 1, because n is a product of those two primes. But nobody can know phi of n efficiently, it's thought, unless they can factor n and compute it that way. So this is private information, and we can pick E such that E has an inverse. Mod phi of n is what you really want, but we know that that amounts to picking E such that the GCD of E and phi of n is equal to 1, which is easy to do. Usually E is some fixed number like 3 or 5 or 7, and there are some more exotic ones that we'll talk about some other time. All right, great. So what do you do with that? So E is public information. Everybody gets to know that. Of course, to generate the parameter safely, you also have to know P and Q, but once you generate E, you can reveal it to the public. So there's another piece of private information, which is called D, and D is E inverse mod phi of n. So it turns out that just from knowledge of D, you can recover the secret. So you can never reveal D to anyone. Just as a sort of aside, how could revealing D be bad? Well, you know that E times D is congruent to 1 mod phi of n. That's just what it means to be an inverse. And so that means there's an equation here. E times D is actually equal to, I need some weird letter, let's say R, R times phi of n plus 1. And look at all the things that are known here. So E and D are known, and 1 is known, of course, and there are not that many possibilities for R. Anyway, you can solve for phi of n here, and once you know phi of n, then it's very easy to know P and Q, and so you have to keep D private. So in our list of private information here, I'll add D, and it doesn't hurt to include all the public information as also part of the private key. So this collection of information here is sort of the private key. Okay, that's what Bob needs to decrypt, and this is the public key. This is what Alice needs to encrypt a message to Bob. And all of these numbers are particular to Bob. This is Bob's private key, and this is Bob's public key. Okay, so how can Alice use all this to send a message to Bob? So what is a message? A message x is just going to be an element of z sub n. So in other words, it's just some number between 0 and n minus 1. And so to encrypt it, she uses the public exponent. Y is computed to be, x to the e mod n. Okay, so anybody can compute that. Here's Alice, and she's sending, y in the clear so the adversary can observe y. And so what makes this strong is that there's no way to discover what x was from y unless you know d. But Bob, of course, does know d. And so when Bob gets y, he does this. He raises y to the dth power mod n. And it turns out that y to the d is congruent to x mod n, and therefore Bob has received the message, but nobody else, including, well, Alice knows what x is because she encrypted it, but she couldn't recover x from y, and nobody else could either because it requires knowledge of p or q or d or phi of n. By the way, knowing any one of these will tell you all the rest. If you know phi of n, then you can figure out everything. If you know either p or q, you can figure out everything. If you know d, then you can figure out everything. So those are the things that really have to remain private. And now there is the dreaded proof of correctness. Dun dun dun. Shall we give an example before we do proof of correctness? Yes. So let's say that, man, everybody uses the example of 15, but I'm going to stick with n equals 35. And so p is equal to 5 and q is equal to 7. All right, and we need to pick, so what is phi of n? This is part of the parameter generation process, which is done by Bob. So Bob knows that phi of n is 4 times 6, which is 24. And so he picks some e, which is relatively prime to 24. And why not just pick the easiest one that works? So e is equal to 3. This is, how does 24 factor? 24 is 2 to the third times 3. Oh no, 3 doesn't work, so we have to do 5. Okay, so that's because it has to be relatively prime to 24. So we'll use e equals 5. Okay, so now we can publish this information and everybody can know that n is 35, and we'll tell everybody that e is 5. Okay, and on the next page, let's send a message. So n is 35 and e is 5. And let's say we want to encrypt the message x equals 20. Okay. All right. So the ciphertext will be y equals x to the e mod 35. So we need to compute that. By the way, this modular exponentiation is slow for us, and it's also slow for computers. This is what makes RSA slow, like all known public key crypto systems. It's a little bit slower. So we have to compute 20 to the 5th power mod 35. So if we want to, we can do something called the Chinese remainder trick here to work in, z mod 7 cross z mod 5. But let's just do it using our brains. So clearly 20 is congruent to 20 mod 35. And now let's square both sides, and we get 20 squared is congruent to 400 which is congruent to, can you figure it out? I think I might need to use a calculator. So can somebody please tell me, I'll just use this. What is 200, there's 400, isn't it? 400 mod 35 is 15. And of course I could have figured that out using a sophisticated technology known as long division. What was it, 15? 15 mod 35. Okay, and now I can square both sides again, and 20 to the 4th power is congruent to 15 squared mod 35. And again, I could appeal to the computer, but let me see if I can sort of psych things out here. So this is 3 times 5 times 5 times 3 is 15 squared. So this is 25 times 3 is 75, but 75 mod 35 is just 5. So this is 15 mod 35. Okay, and now to finish, I just need to multiply both sides by 20. So 20 to the 5th power is congruent to 20 times 15, which is what? So let's do the same trick here that we did last time. So we're saying that this is 2 times 10 times 3 times 5, and actually, instead of doing 10, let's do 2 times 5. So 2 times 2 times 5 times 3 times 5. So this is 75 again, which is just 5. So the answer, so this is congruent to 50. Or am I crazy? No, this is 4 times 5, so this is 20. Sorry. All right, and after all that, I don't want to have made a mistake, so I'm going to check my work using the calculator here. So 20, sorry, I'm getting a phone call. 20 to the 5th power. Oh, and it's a stupid scam phone call too. Mod 35 is 20. Okay, so we did all that correctly. All right, so that's the ciphertext. So irritatingly, the ciphertext is the same as the plain text. So y is equal to 20 also. Oh, by the way, we don't know, we haven't computed d yet. So d is equal to 5 inverse mod 24, which is also 5. Oh, of course it has to be. Man, I hate it when this happens. I thought the chances of this would be low, but do you see what's happened here? So how does Bob decrypt y? He just does y to the d, but that's 20 to the 5th because d is also equal to 5, which is 20 mod 35. That's what we just went through, which is actually the correct I mean, it is x, and so everything worked, but maybe we could let's do a different example where that weird coincidence doesn't happen. Let's just change this to 21. What the hell just happened? Go back, dude. Alright, so if you don't want to see another example, I guess you could fast forward. So we've got to do, let me just do this on a separate page. So let's say that x is equal to 21 and n is equal to 35. Oh, so the problem maybe is e and d. So let's change e too. Let's make e equal to 7. Sorry, e equals 7. And so d is going to be 7 inverse mod 24, and so what is that? Can we guess it? Yes, then 7 inverse is 7 mod 24. Man, we're cursed. Can we pick something that's not its own inverse. Maybe 24 is mod 24 is some weird group where things tend to be their own inverses. So I don't like that, so I'm going to try e equals 11. You see, the problem here is that d is the same as e again. So let's make e equal to 11. And now, just to spare you, I'm going to figure out d with the video stopped. Okay, so it turns out the inverse of 11 is also 11. So I'm going to try something else. I'll just get back to you when I find a good one. So it turns out that every element of Z24 star is its own inverse. So we need to work in a different system. So maybe we should just work right here. So let's say P is equal to 11 and Q is equal to 23. Those are both primes, right? Then N is equal to P times Q. What is N? Let's see. So N turns out to be 253. So now let's pick, by the way, Sage can do Euler phi. I'm going to open up a little more space here. So let's do Euler phi of N, which turns out to be 220. So let's make E 7, and let's just verify that the GCD of E and 220 is 1. Okay, so that E will be good. Now Y, let's pick an element X. So X will be equal to something mod 253. So let's say that it's 233. And then Y is going to be, we have to figure out D now too. So D is inverse mod E of 220. And so what is D? D turns out to be 63. Okay. So Y is going to be, can do power mod, right? So it's going to be X to the power E mod N. And let's see what Y turns out to be. Y turns out to be 117. So now it's time to decrypt. So let's do what is Y to the power D mod N is 233, which was X. Where did we say that? Right here. Okay. So RSA works. And I think I'll make a separate video which gives the proof of the correctness of RSA.